Hello guys, welcome back to my YouTube channel. This is the second video of Robot Kinematics series. If you haven't watched the first video, please do watch it. The link will be in the description box below. So in this video, we will look into today's topic, forward kinematics. So basically, what is forward kinematics? It is the process of determining the position and orientation of the end effector when the joint angles are known. So what it basically means is forward kinematics is determining the position and orientation when the angles are known. For example, forward kinematics, it is determining the position of the end effector and the orientation in the xyz coordinate when the angles are provided. So this is the simplified block diagram for forward kinematics. In robotic arm, each joint's position defines how the arm moves in the space, and the overall motion is the combination of all the joint contribution. Joint positions defines how the robot arm moves in space. That is the workspace of the robotic arm. And the overall motion is the combination of all joint contributions. That is, the final position orientation of a robotic end effector depends on all the joint angle contributions. Now let's look into Danavit and Hartenberg parameters, shortly known as DH parameters. These are the ways to describe the geometry of robots' joints and links. Okay, so robots often have multiple joints and links, and to control the robot, we need to know how the position and orientation of each link changes as the robot moves. So there are 4 different parameters if we consider between two links, namely theta, A, D and alpha, and these 4 terms or parameters have their own different meaning. Firstly, let's look at theta. Theta describes it is the angle between the x-axis of 2 consecutive frames measured about the common z-axis. So for a rotational joint, this will vary as the joint rotates, and for prismatic joint it remains constant. So theta varies for a revolute joint, okay, varies for revolute joint, and it remains constant, okay, for prismatic joint. And nextly we will look into the D, that is the offset. It is the distance between the x-axis along the common z-axis. This describes how far apart the links are along the z-axis. It gives the distance between the links in z-axis. We will understand them better when we start solving the example problems, which will be covered in the further videos. So next comes with the A, link length. This is the distance between the z-axis along the common x-axis. This represents the physical length of the link. This represents the physical length of the link. So next comes the alpha, that is the twist angle. So alpha gives the twist angle between the z-axis of two consecutive frames measured about the x-axis. This represents a tilt between the two z-axes. Represents the tilt between two z-axes. Okay. So now let's look into the transformation matrix. So transformation matrix, it describes the rotation and translation of a link relative to the previous one or the next one. So let's draw an example transformation matrix using 4 DH parameters as shown here. R gives the rotational, position, and 0 and 1 identity. So let's draw an example 1. So Ti is equal to, so I will be using abbreviation for cos as C and for sin as S, and C theta I, that is cos theta I minus S theta I, and C alpha I, and S theta I and S alpha and A cos theta. This will be a 4x4 matrix which gives the transformation matrix between one link to the next link. S theta I, C theta I, and C alpha I minus C theta I and sin alpha. Here comes the di, 1, C alpha I, S alpha I, 0, 0, 0, and zeros. So this matrix shows how to go from the coordinates of one link to the coordinates of the next link in the robot chain. It includes both the rotational, that is the orientation, and the translational, that is the position of the next link relative to the current link. Using this matrix, the robotic arm can be set to the desired position and orientation using these joint angles. So in the next lecture, we will give an introduction to the inverse kinematics. So thank you for watching this video.